Hello everyone. In this video, I'm going to be going over one particular nonlinear model, differential equation model for constrained population growth. So if a population, were growing in a certain area, but due to a certain lack of resources or land area or something like that, there is only so many people that the area can hold, otherwise known as a carrying capacity. This model is called the logistic equation. And I'm going to go over first off what the logistic equation looks like, a little bit on how to solve the logistic equation, and then I'll get into some examples. All right, so my examples are actually coming from a textbook, so I didn't write it out on paper. So I'll actually get into this example that's on this page you're seeing right now after I talk about the logistic equation itself. Okay, so let's talk about the logistic equation. All right, and it is a first order nonlinear equation. And it looks like this. All right, so say now in my discussion of the logistic equation, I'm going to have the population, it could be people or, amount of bacteria or amount of people that have heard a rumor or amount of people that have a disease. You might see examples where this is a different thing, but I'm going to have P of t represent the population at time t. Okay, where again t could be in units like years or months or days or seconds, whatever the units are in the particular problem you're looking at. Now the logistic equation takes on the following form. It is dp dt. Okay, so the rate at which the population is changing over time is equal to P multiplied by A minus BP. So two factors here, one P times A minus BP. So this is saying that the rate at which the population is changing is equal to the population at the time multiplied by some quantity minus some multiple of the population at the time. All right. This A and B, okay, are constants. A and B, in the A minus BP, are constant factors, and typically it's noted also that they are greater than 0. All right, and you'll see why that is later when I get into the solutions of this kind of an equation. Why it would be beneficial to have A and B be greater than 0. Alright, now you may have noticed, if you've seen other videos I've put out there from previous sections, that this is an autonomous equation in P. Alright. So it's a first order non-linear equation because you'd have the P squared involved there. First order nonlinear differential equation, but also one of those autonomous first order equations, right, where you have your first derivative written as a function solely dependent upon the dependent variable, in this case P. So since it's autonomous, I'd like to talk about that for a little bit. We can find some critical values or some equilibrium solutions. And these are where, dp dt here is just equal to 0. So basically what makes each of these factors equal to 0 here, we have critical values of p equals 0, and then this factor of a minus b p, that would be equal to 0 when p equals a over b. And then along with critical values, you have your phase portrait for this equation. So this vertical line here, let's say, will represent the p-axis if I were making a horizontal axis t and vertical axis p. My critical values, these equilibrium solutions, are again p equals 0, and I'm going to be assuming that a and b are positive constants, so a over b is also positive. P equals a over b. And then plugging in certain values here. If I plug in something bigger than a over b, then we'll have negative values of dp dt. So slopes will be sloping downward. Functions up here will be decreasing. Between say I put half of this, then you'd have positive value be increasing. You'd have positive derivatives in between this band. And if I were to, for some reason, plug in the value of p, have p equal some constant less than 0, then this would be negative, and b being negative, this would be minus a negative or a positive. You have a negative times positive, you'd have a negative result for dp dt. So we'd see that this p equals a over b is an attractor. Right, an attractor. This p equals 0 would be a repeller. And some typical solutions, right, some typical solution curves to an equation of this nature would look like the following. Solution. So that's the time axis, and then the population. Here's p equals a over b. Here's p equals 0. We're going to be focusing mostly on this area here between p equals a over b and p equals 0, because I don't want to talk about we're not going to be, usually most real world scenarios aren't going to have things where there's negative populations. And in this band, you have something like this typically as a typical solution curve, where at time equals 0 you have some initial population, say p sub 0, and say p sub 0 is the initial population. And then the population grows, kind of almost exponentially at first. It grows at a fast rate, but then at some point, still growing, but growing at a much slower rate, and coming in underneath this p equals a over b. Because again, due to land constraints or resource constraints, or maybe diseases or famine or whatever, population grows fast, quickly for a little while, but then eventually, due to certain constraints, the population starts growing more and more slowly. This a over b is sometimes referred to as the carrying capacity. It's like, in this particular land or whatever, the population will never exceed a over b. Right? And if it were, that would be catastrophic. There's not enough land, not enough resources to support more than that many people. Okay, so that's the start of looking at this, as an autonomous equation. Now I'd like to actually talk about, what was solutions, how to go about solving such an equation. And hopefully you can also see that such an equation is also separable. Right. So that'll be the next part, solving the logistic equation. So I'd separate the variables, right? Get all the all the p stuff to one side. So I would just simply divide by both these p factors. So we'd have dp over p times a minus bp, and then put the dt on the other side. You'd have equals 1 dt. And I'll make it an initial value problem as well. I'll also mention that p of 0, say the population at time 0, is labeled as p sub 0, okay, as I mentioned up here. All right. So now I've separated the variables. Let me integrate. All right, so I'm going to not do every little step in this video. I don't want it to be too terribly long. But on the left side, we'd have the integral of 1 over p times a minus b times p dp, and again, I'm not going to go into this, but I would use a method here of partial fraction decomposition. Hopefully you recall this from maybe a Calculus 2 course. So you would break up 1 over p times a minus bp into the sum of two fractions, one with a denominator of p and the other with a denominator of a minus bp, and you'd end up with this. So again, not going through all the steps, we'd end up with 1 over a times the integral of 1 over p dp plus, and then little b over a times the integral of 1 over a minus bp dp. All right, so again, I leave that to you to be able to get that through partial fraction decomposition. All right. Then after actually integrating, we'd have 1 over a times the natural log of the absolute value of p plus b over a. Well, actually, 1 over a again, because if I do some substitution here, the b would go away, and then I'd have minus, so my apologies, minus 1 over a. So that's a 1, sorry, minus 1 over a times the natural log of the absolute value of a minus bp. And again, you can double check, make sure the derivatives of these things are what we have up here. Again, sorry, this is a 1. And then you can put plus some constant, but I'll do it on the right side of this. Okay, so then the right side, that's really easy. The right side would just be the integral of 1 dt. So that'd just simply be t, plus some constant. So again, I'll just say plus c. All right, so now I have this. And I'm going to do a little manipulation. This expression on the left side with the logarithms, I'm going to use some properties of logs here. We have 1 over a factored out. They both have 1 over a in common, times the natural log of p divided by a minus bp. Okay, and this should be equal to t plus some constant. Again, c is constant here. And again, bear with me. There are going to be a lot of letters involved here. But once I get the general solution with all the letters, then I could look at any equation that's of the logistic nature, and just plug in some numbers. I can skip right to the solution without having to go through all this again. All right, well, multiplying both sides by a, you get the natural log of p divided by a minus bp equals at plus, ac. Now I know ac is another constant, but I'm going to leave this like this for now and keep going. My goal here is to eventually solve for p, right? Get the population alone. All right, then I would exponentiate both sides, right? With base e. Pardon me. So we now have p divided by a minus bp equals e to the at plus ac power. All right, and then I would multiply by this, get all the stuff with p to one side. So again, I'm going to skip a lot of the algebra and eventually end up with this, where I'll multiply by a minus bp, distribute this e factor, and take all the p's to one side, factor p out. We'd have p times the quantity 1 plus b times e to the at plus ac power equals a times e to the at plus b plus ac power. And then I finally divide by this, and then we're going to keep messing around. All right. So p of t, right, when I finally solve for p here, I'm dividing by t. P of t equals a times, now here's where I'm going to kind of fudge with this a bit, e to the at plus ac, that's e to the at times e to the ac, and all of these, e and a and c, are constants. So I'm just going to call that k, right, for constant k. So keeping that in mind, again, please bear with me here. If you want to pause things, slow down, go back, whatever, be my guest. So I have a times k, right, times e to the at divided by, and then 1 plus b times this k times e to the at. All right. Now I could also figure out what this k is. All right. Remember that I said p of 0 is going to be called p sub 0. All right. So what we have now is the following. All right, using the condition. Maybe I'll do this in a different color so we know it's a separate thing. We'd have p sub 0 equals, a times k times e to the 0, so just ak divided by 1 plus bk. And then again, saving some time here, if you were to go through and try solving for k, all right, you'd end up with k equals p sub 0 divided by a minus b p sub 0. All right, so I'm going to put that in to get a more full model. So p of t equals, a times k, p sub 0 divided by a minus b, p sub 0, times e to the at, divided by 1 plus, b times this k, p sub 0 divided by a minus b, p sub 0, times e to the at, and then one final move I'm going to make to get the model to be in the same form that you'll see in a lot of books, especially the Zill's 11th edition textbook, if that my course is using for this video. I'm going to now multiply the numerator and denominator here by the quantity a minus b times p sub 0 times e to the negative at. Right, I'm going to do that to the denominator as well. A minus b times p sub 0 times e to the negative at. And then finally. All right, so again, sorry about this. This took a while, but it'll be worth it when we get to some examples. So the final model, all right, for the solution of the logistic equation, P of t equals just a times p sub 0 divided by, and then, if I multiply this by this term, you just have b times p sub 0. I'll put that first. Plus, and then this times 1 would be itself, right? So plus a minus b times p sub 0 times e to the negative at. And I'll put this in a nice box because I'm going to refer back to this when we go about looking at the examples I'm going to look at. Right. So remember, this is a solution to the following IVP. Right? That dp dt equals p times a minus b p, with p of 0 being p sub 0. Right. Okay. So if we know all this information, if we know what a and b are, and again, I would like a and b to be positive quantities here. If we know what a and b are, and this initial condition, this p sub 0, this initial population, we can jump straight to this solution. Right. Now, look at what happens to such a model. All right, this is a weird looking, there's kind of like an exponential here. Right? We're looking almost rational with an exponential function in it. Look at what happens to this function as time goes by. What's the limit as t approaches infinity of this solution model? Well, the numerator is a constant, right? A and p sub 0 are constants, so that's going to stay the way it is. So a times p sub 0, and this is a constant, b times p sub 0, plus, and then this is a constant as well, but then e to the negative at. Right, that e to the negative at part of this second term in the denominator here, this approaches 0 as t gets huge, right? Especially if a is positive. If a were negative, it would blow up to infinity. But so this term goes to 0, and we're left with a p sub 0, b p sub 0. The p sub 0s would cancel, and you get a over b, right? Then that was that carrying capacity that I mentioned earlier, right? The population will grow and grow and grow, but it doesn't exceed this amount. This is going to have a graph looking like this. Again, this is p, this is t, and I had this up earlier. Here's a over b, and the population will start at p sub 0, grow quickly early on, and then start growing more slowly and tapering off and leveling off, approaching a over b as time goes by. Okay. All right, so that was a lot. All right, that was 20-some minutes there of just introducing the logistic equation. Now let's just get into an example. All right, let's get into an example where this is used, or where a logistic equation comes up, and I'll keep referring back to this, our solution here. All right, so in this question I'm looking at, you see the number now, instead of p of t, it's n of t. Still for some population, but not of people. It's for supermarkets throughout the country that are using computerized checkout systems. And this is described by the initial value problem that. Now you see how this is got that same form as the logistic equation. The dn dt equals n, times the quantity 1 minus, 0.0005, 5/10,000ths times n, or 1 over 200 times n, or 1 over 2,000. Sorry, 5/10,000ths is 1 over 2,000. And then the initial population, right, the initial number of supermarkets throughout the country that use a computerized checkout system is 1. Okay. So now in part A, well, first let me go back to my paper and write this out. All right, so we have n of t instead of p of t. Right? N of t is this number of supermarkets. I'll just say number of markets with computerized checkout at time t. And I'm pretty sure t will be in years, but we'll get to that in the later parts of the problem. And the IVP we're given is, dn dt equals n times 1 minus, 0.0005 n, and the initial condition, right, n of 0 equals 1. All right, so you see here, this is exactly like our logistic equation, right? Instead of n, though, instead of p, I have n. So you see there's n's instead of p's. And it's in the same form. You have n times a minus bn, and then n sub 0 is 1 here. So the value of a is 1. The value of that little b is 0.0005, or 5/10,000ths, which would be 1 over 2,000. Right? And then n sub 0 instead of p sub 0 is 1. Okay. So we'll come back. So we can go recognizing that this is in that same exact form. I'm going to jump right to the solution when they ask for it in a second here. But the first part is about, hey, remember this is an autonomous equation. So part A, use the phase portrait concept. Now it says of section 2.1. That was on those in this book I'm looking at. That was on the autonomous first order differential equations. To predict how many supermarkets are expected to adopt the new system, the new procedure over a long period of time. And by hand sketch a solution curve to the given initial value problem. So here's what they're talking about there. Right. So remember the critical values, this is an autonomous equation, would be n equals 0, and what would make this second factor equal 0 is n equals 2,000, because 5/10,000ths again is 1 over 2,000. So times 2,000, make this 1 minus 1, which would be 0. And then the phase portrait, right, here's the number of supermarkets thing here, n equals 2,000, n equals 0, would look just like the phase portrait I had earlier, where n equals 2,000, and you can test this out yourself, would be an attractor, and n equals 0 is a repeller. And so our typical curves here, our typical a solution curve would be like this. Here's 2,000, and n of 0 is 1. And so it starts off here at 1 as time goes by. There's time 0. There's one store with computerized checkout. And then what I would suspect would happen would be, that amount grows and grows and grows, but then, you can only have so many. After a while, the growth rate will start slowing, and it looks like it'll max out around, until before it hits, 2,000 stores. Okay, hopefully that makes sense. And again, this is all basically the same as what I was showing you earlier with all the letters, with A over B and stuff like that. All right, because A over B in this case is 2,000, your carrying capacity. All right, then, question B, part B of this question, solve the initial value problem, and then use a graphing utility. I'll use the Desmos slope field generator to show you that indeed the solution we get will be a good solution to this differential equation. And then how many companies are expected to adopt the new technology when t equals 10? All right. So again, very simple. I solved it in general already, right? The logistic equation. So that was here. Right, remember, if our initial value problem looks like this, which this one does, looks exactly like this, but instead of p you have n. I've already solved such an equation. Right? I just need to replace a with 1 everywhere I see b with 1 2,000th, and everywhere I see p sub 0 with n sub 0 with 1. Right? So plugging those in, the solution to this initial value problem is the following. N of t equals, I'll put that back up. We'll refer to the formula I found earlier, the model we found earlier. So again, it's a times p0. So a was 1, p0, which is n0 here, is also 1. So 1 in the numerator. Now b times p0, b is 1 2,000th, or 0.005, right? I'm going to write it as 1 2,000th times p0 is 1, plus a minus b p0, so the quantity 1 minus 1 2,000th times e to the negative at, or so just e to the negative t, right? Because again, a was 0. And here we go, and just to make this look a little neater, right, because I got kind of compound, I'm going to multiply the top and bottom by 2,000. Right, so we'd have 2,000 in the numerator, divided by 1, plus, and this will end up being 1999. All right, 2,000 minus 1 when I multiply that by 2,000, so 1,999 times e to the negative t. Right. And you see how this actually satisfies the initial condition. Right? If I replaced t with 0, you'd have 1 plus, you'd have 2,000 in the numerator, 2,000 in the denominator, so you'd get 1 as your initial population, initial number of supermarkets with computerized checkout. And as t goes to infinity, this term down here, the 1999 e to the negative t, that would go to 0, and the population would be approaching 2,000. And let's take a look at this. Let me actually show you. I'm going to go back to the websites and pull up. This is the slope field generator in Desmos. But instead of n and t, we have y and x. So everywhere, and instead of n, I'm going to use y, and instead of t, I'm going to use x. Right? So I'll put up the slope field first. Right? Y times 1 minus 0.00. Actually, this might not look too great because I know the slope field doesn't go up to 2,000. Yeah, because obviously whoever made this only went up to 10. Anyway, let's just graph our solution. So y equals, n equals, and I said it was 2,000 divided by 1 plus 1999 e to the negative, negative x instead of negative t. Okay. Now you can see that in the parts that actually have slopes, right, the slope field is working out. See this green solution curve, every time I move a point onto that curve, the slope is pointing in the direction of the curve. It actually fits the slope field really well. Now if I scroll out, I have to scroll out quite a bit here. See how the population is increasing rapidly in the beginning, for small values of t. But then as t grows up, it's larger and larger, and maybe I should change the window up. Yeah, let's do this. Have the y-axis go to max out at 2,000. And maybe have the step be every 10 or something. Alright, that's not a great graph. And bump up the x-axis values as well. Let's have that go out to 1,000, say. Okay, you know what? I'm going to find a better calculator. Just a second. Alright, so sorry about that. I'm back now, and I just put it on my graphing calculator. So I put in y equals 2,000 divided by the quantity 1 plus 1999 e to the negative x. And the very top of this window is 2,000, and you can see again the graph increase, the number of stores increasing very rapidly early on, but then after time tapers off, levels off at this 2,000 level. All right, like I was drawing here, but much steeper. All right. Okay. So again, I'm sorry I didn't have a great calculator on the website. Now, I mean, you could make a nice little table for this function and see that as x goes to larger, as the value of x gets larger and larger, right? 100. See, it's so close to 2,000. It's just saying it's 2,000. Yeah. Okay. Oh, and here we go. They actually filled it in. It just took a while. See the part of the graph now? It shot up rapidly and then levels off right beneath 2,000. Now, it never actually hits 2,000, mind you. 2,000, it's just so close to 2,000 that it says it's 2,000 after a certain point. Okay. And then the question is, how many companies are expected to adopt a new technology when t equals 10? Well, that's just plugging in 10 for t and have 2,000 divided by 1 plus 1999 times e to the negative 10. So let's go back to my calculator here for you. And yeah, see, I got the function there. Go to a table. And yeah, when my input is 10 here, the output is 1,000, about 1,833 or 1,834 stores. All right, so I'll write that down. N of 10 is approximately 1,800 if I round to the nearest store or supermarket. Okay. Great. So again, hopefully, again, that was a long start to the video where I went through and solved, the logistic equation and found the general solution here. But once you've got this, you can then go to any logistic equation and plug in all your values, and you'll have the solution right away. So I'm going to do this just one more time with one more example. Okay, so it's this question here. Another logistic equation is given to us, so if that's the case, I can jump right to the solution. A model for the population, now this time it's P instead of N. The population P of T in a suburb of a large city is given by the initial value problem. And you see how it takes on exactly that same form. dp dt equals, P times A minus BP, where A is 1/10, right, 10 to the negative first. And B is 10 to the negative 7th, which is 1/10,000,000th. Right. And the initial condition P of 0 is 5,000. And here T is measured in months instead of years. What is the limiting value of the population? Well, remember, that's that carrying capacity. That'd be just simply A over B. 10 to the negative first divided by 10 to the negative 7th, which would end up being 10 to the 6th. So 1,000,000 people. Right? One with 6 zeros after it. And at what time will the population be equal to half this limiting value? Okay, so we can answer that question, using our model. So going to another piece of paper, and I'll write this information out. So this time, again, P of T represents the population of some suburb of a large city, and dP dt is P times 10 to the negative first minus 10 to the negative 7th times P again. And the initial condition, P sub 0, is 5,000. So I've got everything I need. All right, I've got everything I need. It looks exactly like this. I put in 10 to the negative first for A, 10 to the negative 7th for B, and 5,000 for P0. So yeah, so the solution to this IVP we can jump to right away is P of T equals 10 to the negative first times 5,000, which we'll simplify this in a second, of course, divided by 10 to the negative 7th times 5,000 plus, and then A 10 to the negative first minus 10 to the negative 7th times 5,000 times E to the negative 10 to the negative first T. All right, just replacing all the A's with 10 to the negative first, B with 10 to the negative 7th, and P sub 0 with 5,000. Okay, now that carrying capacity, I guess you could leave it like this or simplify it if you wished, but yeah, actually I'm going to multiply the top and bottom here. I'm going to multiply the top and bottom by just 10 to the 7th. Just to get rid of that 10 to the negative 7th. And we'll see what happens. So the numerator would simplify to 10 to the 6th times 5,000. Then down here we'd have just 5,000 plus, then multiplying these by 10 to the 7th, we'd have 10 to the 6th minus 5,000, and then e to the negative, 1/10 t. I'll just replace 10 to the negative first with 1/10 because that's what it is. All right, same thing. Now that carrying capacity, that limiting value, all right, the carrying capacity is just, what's the limit as t approaches infinity of the population, right, of this population function. Now remember, we said this was just a over b. This will end up being just 10 to the 6th, so you can see that here, right? If I let t approach infinity in this solution, this term down here would go to 0, right, the term I just circled, that would go to 0, and then the 5,000s would cancel. I'm getting 10 to the 6th, or 1 million people. All right, then the following question is, at what time will the population be equal to half this limiting value? So the second question is, when is the population equal to half of 10 to the 6th, right? Or 500,000 people? And you're just solving an equation from this. All right, now it's going to look a little weird. It's pretty funky, but still like any other exponential equation we'd have on the left. Just go into this model. Want to know when is half of 10 to the 6th, or 500,000, equal to 10 to the 6th times 5,000 divided by 5,000 plus 10 to the 6th minus 5,000 e to the negative 1/10 t, and we're solving this for t. So I mean, me personally, I would start off by maybe flipping both sides and multiplying by 10 to the 6th times 5,000. So I mean, if I flip both sides, I'd have 2 over 10 to the 6th here. All right, flipping this equals, and then 5,000 plus 10 to the 6th minus 5,000 e to the negative 1/10 t over 10 to the 6th times 5,000, and then multiply by this denominator. The 10 to the 6th would cancel, and I'd have 10,000 now on the left equals 5,000 plus 10 to the 6th minus 5,000 times e to the negative 1/10 t. And then I'm just basically trying to isolate this e to the negative 1/10 t. Right. So hopefully I'm not going to work all the algebra out here. That'll take a while to write out every single little step. But if I subtract 5,000, that'll be 5,000 there, and divide by this, then take the natural log and multiply by negative 10. So I'd have negative 10 times the natural log of 5,000 divided by 10 to the 6th minus 5,000. And there we go. That's how long it would take for the population to reach 500,000 people, right? Half the carrying capacity. Now if I punch this in, so we got negative 10 times the natural log, 5,000 divided by the quantity 10 to the 6th minus 5,000, and all that in the log there. Yeah, so about 52 months, almost 53 months, approximately 52.9 months. Remember, time was in months for this particular question. Okay. So yeah, lots to do there, lots to think about. But if you know the basic solution to the model, right, like I had here, going back to this, if you've got this down, you can really just plug and play. And also remember what they mean by limiting population or carrying capacity. That's what happens to the population as time goes to infinity, right? As time blows up. kind of like a horizontal asymptote, really, for the graph of the population model. And in some other exercises you may come across, you might have to find the values of this a and b. You might have to find the values of these constants. And if that's the case, you're going to have to set up systems and solve those systems. Yeah. So I'm hoping at least seeing these couple examples, right? And also that introduction, that first 20 minutes of the video. Again, I know this is a long one, but that first 20 minutes of this video, introducing you to the logistic equation and its solution. And I'm hoping all that stuff will help you when you work on other problems related to the logistic equation itself. All right. And again, I'm sorry how long this was, and I had a couple snags there with the slope field generator and the graphing calculator, but again, hopefully this helps. All right. Thank you very much for watching.